Sorry, I missed the starting time because I was talking to one of your classmates. Okay, so if you have questions, please do ask me. And I'm trying my best to answer the questions. Okay, so now let's talk about the lectures. So last time we are talking about logic, and then from logic we move on to set, right? Now, during the lectures, we mentioned Russell's paradox, and then we said what it is, and then we changed topic to more standard things. Now, here I want to maybe spend another 5 to 10 minutes on the paradoxes. So I want to tell you a little bit more about the background. So why do people care? How does these things come from? So this is, to me, this is interesting because this is about the nature of mathematics, right? So we are in the general education module, although we don't need to know lots of details, but I hope you'll see some picture about mathematics as a whole, right? So that's why I want to spend some time on this. But on the other hand, obviously, we cannot get into details. So these are called digression. It means this material will not be in the syllabus. So it's just for fun. Okay, so the background. So why do Mr. Russell or Lord Russell come out with this paradox? So the background is we have to mention another philosopher or mathematician, Frege. So he's one of the greatest philosophers. So he holds the view that mathematics. Okay. So let me remind you one thing. So when we talk about logic, so I think I was mentioning people usually believe mathematics is safe. You cannot make mistakes because all the mathematical truths are solid, right? So the question is why? What gives mathematics this feature? So Frege is trying to defend mathematics, trying to justify this view. So he was saying that mathematics is safe because it comes from logic. So this in philosophy, you always have this ism or that ism. This is called logicism. You believe logic is everything. So Frege believes that mathematics was grow from logic. So you start everything from logic, and then in logic we believe that the basic truths, right? The axioms are basic truths, and the rules preserve truths. So that's why anything you derive from logic is true, is safe, right? Now mathematics is coming from logic, so therefore mathematics is safe. So he was holding this view. So actually he carried out this development. So he wrote books about how to derive everything in mathematics from the very basic things about logic. So he wrote, he finished the first volume. He tried to finish the second volume, but this time that Russell sent him the paradox. So because he was trying to develop everything from the basic concept like sets and so on and so forth, but he used this naive view of sets. He believed that any property will give you a set. And then Mr. Russell says, no, if you believe that, actually your theory is not safe. Your theory actually is wrong. There's a contradiction inside. Look at the Russell's paradox, right? If you should I go back to right here. So we mentioned the rules 1 and 2, right? So if you just believe 1 and 2, you think you are safe, but actually no. Russell point out, just based on assumption 1, assumption 2, you get a contradiction. So therefore, it's not safe. Okay. So so now we come back to Russell. So he sent a short letter to Frege pointing out this paradox. Actually, his letter was very, very polite, right? It's not saying you are wrong. He says, okay, you have done great work, and I admire your work. Everything you have done was so great. There's just one tiny thing I don't understand. The tiny thing is that paradox. But unfortunately, the tiny thing somehow ruined the whole project of Frege. Okay, so that's why I have the two pictures here. So the Russell's paradox comes from this discussion. Okay, so now what happened? So now we see a problem in naive set theory, right? So obviously something has to be done, right? So after Russell's paradox, what are the ways to get rid of paradox? So there are several proposals. Russell himself has developed some type theory and so on and so forth. But nowadays, one of the standard approach is to add axioms we change naive set theory to so-called axiomatic set theory. So in other words, you add more conditions on things to be called set, right? So the lesson learned is not every collection can be called a set. If you call every mental collection a set, you would have this problem, because you see the trouble comes from, for any property P will give you a set, right? So that is wrong. So we have to add some more restrictions. Say only those things satisfy the restriction can be called a set. All other things you cannot call it set. You can call it collection, fine, but don't call it set. You cannot do the usual mathematics to those things, right? So you add conditions. Only those satisfied conditions are qualified to be called set. Okay. So by doing this, by adding these conditions, the paradoxical set collection Russell proposed was removed. Right. So now this funny R, although I write it like this, is no longer qualified to be called a set. So he's gone. So therefore, at least nobody find any new paradox. Okay. Now, so the axioms or the conditions to add, they are standard collections. So it's called ZFC or ZFC. So Z is coming from Zermelo. He's a German mathematician. Franco also. So the Z comes from Zermelo, F from Franco, and C is not a person. C is a name of axiom called axiom choice. Comes from the word choice. So there are 9 schemes. Each scheme could have infinitely many axioms, but of the same pattern. So you have 9 collections. Some of them are just one sentence. Some of them are longer, have infinitely many sentences. So this becomes standard. There are alternatives, but this is more common in mathematics. Now, you may ask this, although no more paradoxes are found, maybe because we are stupid, right? So maybe another Russell, somebody so clever that when they look at this ZFC, they'll find some other paradoxes, right? So the question becomes, now you claim you have ZFC. Is ZFC safe? Does it contain contradiction? Okay. Okay, so then, these all happens 100 years ago. Okay, so in the early 20th century, so there are two schools of, I'm going to mention two famous persons. So David Hilbert is a famous mathematician. So he is interested in foundational mathematics, and he proposed a plan. The issue was, is mathematical safe? Is ZFC safe? Right? Maybe there's also contradiction. How do we make sure that there's no other paradoxes, right? So Hilbert proposed maybe mathematics can prove, right? Mathematical is safe, right? So because in mathematics we believe proofs. So everything, no matter how many examples we discovered, we don't believe this is universal. This is, to say something is true, we have to prove it. Right? We have to give logical reasons to show something is true. So Hilbert was suggesting that maybe mathematics could justify itself. Maybe we can use mathematical means to show we are safe. Okay, here I'm not so accurate. So actually, his proposals are more complicated than this. But this is a general education, so let's don't be bothered about the details. Okay, so he was trying to give a proof, saying I can show you that mathematical is safe. Okay, then he has this famous so-called Hilbert program, trying to justify mathematics. There's no contradiction in mathematics. But his plan, unfortunately, cannot be carried out as he imagined. So there's another famous logician or mathematician, Gödel. Gödel showed that his plan cannot be carried out. So so now let me repeat what I just said. So Hilbert trying to prove mathematics is safe, right? So maybe the set theory can show itself is safe. Okay. But Gödel showed his very famous incompleteness theorem, saying that any reasonable mathematical system, formal system, cannot prove its own consistency. This reasonable, obviously, is not a mathematical word. So there's a mathematical definition for reasonable. So it says if it has no contradiction, and it can say a little bit number theory, can talk about natural numbers, can do addition and multiplication. So this is a very, very minor restriction on the theory. So Gödel showed that any reasonable theory cannot prove itself is consistent. Now ZFC is a reasonable theory, so if ZFC has no contradiction, he cannot show himself is consistent. So it's a very powerful theorem. Essentially, it says you cannot use mathematics to justify yourself. You cannot prove yourself is consistent. Okay, now, although we cannot, so Gödel theorem applies to many cases, we can do something weaker. So we can show some relativized consistency result. Okay, so let me explain this. So ZFC, as I said, maybe it has 9 schemes or 9 family of axioms. Some of them are so obvious that usually people do not question, but some of them are complicated. So usually the people have doubts, right? If you doubt whether there's a contradiction inside, you would look at those complicated part. You don't look at the simple part. For example, for number theory, if you look at, say, x plus y is y plus x for any natural numbers, people will think this is true. They will not question. But if you say some very, very complicated number theoretic facts, maybe that has some problem, right? So the same thing happened to set theory. So in set theory, there are simple axioms, there are complicated axioms. For example, axiom of choice is a complicated one. So people usually doubt those complicated ones has problem. But in set theory or in mathematics, they are relativized consistent results, saying if you assume certain part, if you assume the simple part is consistent, give you no problem, actually we can show that the complicated part is also safe. So the concrete example is this. Some people doubt axiom choice will give us trouble. So they try to avoid axiom choice. But actually people have shown, actually Gödel is the person who showed, that if the set theory axiom without axiom choice, right? Suppose I delete C from ZFC, I only have ZF, right? So I suppose ZF is safe, and then adding axiom choice is also safe. So this is there are some indirect evidence to show mathematics is safe, but ultimately you cannot justify it by using mathematical means, right? So that's what happens after Russell's paradox. Okay, so now the Gödel theorem looks very, very negative. The reading I just had was very negative, but actually there are positive messages to take away. So one positive side is it shows mathematics is inexhaustible, right? So you cannot hope that you just have one system, then after you discover the system, you can show everything in the world. Sorry, I'm trying to justify this, right? So if mathematics, I'm trying to justify mathematics is inexhaustible. So what is the opposite view? The opposite view is we have maybe we have one system of mathematics, and then everything in mathematics can be proved using that system. If that's the case, you just input the axiom into the computer, and the computer will try all the proofs, and then it exhausts all mathematical facts, and then that's done, right? So we don't need mathematicians, we don't need any new discovery. Everything was in that particular system, right? So Gödel's theorem say, no, you cannot have that system. Because if you have that system, he cannot prove everything in the world. For example, he cannot show his own consistency. Right? If you have that system, you would believe that system is safe, right? However, the belief itself is beyond your system. So your system cannot exhaust all truths. So there's always something the system cannot show. Okay. So there's no such dream system which can formalize everything in mathematics. So based on this, what we can do is we try to discover more and more, right? Because there's no end. So what we can do is we try to discover more. No matter which stage we are in, there's always more to discover. So that's so people are still search for the new axioms for mathematics, and the search is still going on. It never stops because by Gödel's theorem, right? So that's the remark about what is the background of paradox and what happens after the paradox. Okay, it takes longer than I thought, but okay. Now, so let's move on. So today's lecture, we are going to continue on the topic of sets, right? So I'm going to remind you some easy topic about set, and in particular, we are looking at some counting. So we count the number of elements in sets and so on and so forth. We also talk about functions. In particular, we'll talk about injective, surjective functions, and so on and so forth. For those who are from SOC in 1231, you have learned this before. I believe in JC, even in JC, you learn some of the facts about sets. Okay, so but before before we talk about sets, I want to give you two number theoretic results. I call it classical examples. So there are famous mathematical facts we believe that everybody should know. So even it's in general education module, even we don't talk about some complicated facts, these things we believe everybody should know. So that's why I want to prove two theorems to you. Okay, you'll probably know this, but okay. So let me talk about the motivation. Why I talk about these two examples and so on and so forth. So first, these two examples are all shown by proof by contradiction. So I want to quote Hardy. He is a British mathematician. He wrote he's a number theorist. He wrote a famous book called Apology for a Mathematician. And this quote and the next one are coming from that book. So the book is written for general audience. So you are welcome to download or to borrow it to read. Okay, so this code is about proof by contradiction. So proof by contradiction, there's a fancy name, maybe Latin, right? Reductio ad absurdum. So this is proof by contradiction. So this is one of mathematicians' finest weapons. It is far finer gambit than any chess gambit. Gambit means you give up some pieces and then you gain some advantage. Right? When you play chess, sometimes you sacrifice a pawn and then to get things, right? So so according to Hardy, he says this is much finer than the chess gambit. So a chess player may offer the sacrifice of a pawn or even a piece, but the mathematician offers the whole game. So you'll see the meaning in the examples. Okay, so now in the same book, he says this. I want to quote the whole paragraph because I want these are the backgrounds for the example chosen. Okay, so let's read this paragraph. So I will state and prove two of the famous theorems of Greek mathematics. They are simple theorems, simple both in idea and in execution, but there is no doubt at all about their being theorems of the highest class. Right? Although they are simple, they are the theorems of highest class. Each is as fresh and significant as when it was discovered. Right? 2,000 years have not written a wrinkle on either of them. Okay. Finally, both the statements and the proofs can be mastered in an hour. Okay, so we will master them in 20 minutes. Okay. In an hour by an intelligent reader. But NUS student is much better than an intelligent reader. So, however slender his mathematical equipment. Okay, so we are going to see these two. Okay, here's the Greek. There's a the painting is by Raphael. It's in Renaissance, but the picture describe the school of Athens, right? So we are going to look at some figures, Euclid and some other people. So you know this picture, right? This is Vatican. So the two center figures, one is Plato, one is Aristotle. So it talk about the great time in maybe in human history. Okay, so the first theorem is this, is to show the irrationality of square root 2. So we are going to show there is something called, there's some, so we know what is rational, right? Rational numbers are the ratios of two integers. So the claim is they are irrational numbers. They are numbers which you cannot write them as ratio of two integers. For example, this square root 2 is the example. So the example, so the statement says there exists no rational number whose square is 2, right? So therefore, the square root 2 is a irrational number. You may wonder, how do we know square root 2 exists? Right? Why it is a number at all? Well, in Greek times, they have lots of knowledge on geometry, right? So the lots of numbers are expressed as the length of some geometric figure. So square root 2 is the diagonal of a unit square. So you can draw a square with side 1, and then the diagonal is square root 2. So you see, you draw a square, and then the diagonal must exist. If it exists, it has a length. So what is the length? So there must be a number, right? So that's why we know there is something called square root 2. So we want to show that this square root 2 is not a rational number. You cannot write them as a ratio of two integers. Okay, so let's look at the statement slowly. So it says, in other words, this square root 2 is irrational, right? Because no rational whose square is 2. So which is known to the followers of Pythagoras in around 400 BC. So this is a small picture, small part in the School of Athens. This figure supposedly is Pythagoras. Okay. So in symbols, we need to show that, okay, so this is negation. So it's not the case there's a rational number, x, whose square is 2. Right? So I'm writing it in symbols. So which is equivalent to say for all x in rational, x squared is not 2. I'm saying the same thing in different ways over and over again. Right? So you're here. But suppose I'm giving you this task to show every rational number whose square is not 2. It's very hard to show. Last time, I think we have seen this, because to justify a universal statement, you have to look at every possible instances, right? You want to say for every rational something happens. You have to check every rational on the face of it, right? But there are so many rational numbers. How can you check it, right, in 20 minutes or in 1 hour? So it's not easy to start. Okay, so that's why we try to prove by contradiction. Okay, so at least we can start with something. So we prove by contradiction. So let's begin with the negation of the statement, right? So let's begin with suppose it's not the case, right? Okay, so here we want to show it's not the case. We want to show a negation of something. Now if you negate this, you just delete this, right? So you have double negation, but double negation is as the original one, right? So if you assume this is not true, and then actually you are assuming the following: suppose that there is a number, a rational number x, whose square is 2. Right? Let's see what's happened. Okay, so we can start with something, with this x, which is rational, and the square is 2. Okay. Now, what is the meaning of x is irrational? Well, I said it many times now. So x can be written as a ratio of two integers, right? So it's like a over b, and then this x square is 2, right? So you have a square over b square is 2. So in other words, a squared is 2 times b squared. Okay? So far so good, right? So then the claim is a has to be an even number, right? Because the right-hand side is even. It's a multiple of 2. So a has to be a multiple of 2. Otherwise, you have no factor of 2. So a has to be even. So if a is even, a is a multiple of 2. A is 2 times something. A is 2 times m for some m, right? So we have 2, okay, this is a, 2 times m, whose square is 2 times b squared. So we get 4 times m squared is 2 times b squared, right? So then we get 2 times m squared equal b squared. Cancel a copy of 2, you get this. Okay? Okay, now apply the same logic. Now this time, b squared is an even number because he is a multiple of 2, right? So this b is even. Wait, but now we have something funny, right? Because in this case, both a and b are even. Now why don't we start with both of them are even? We can cancel out the common factor, right? So we can start from the lowest terms, right? So if both of them are even, we first process, cancel the common factor, and then start, right? So here is the analysis, the discussion about the proof. So now I'm going to turn this around to write it properly as a mathematical proof. Okay, so I hope this is clear. Right? Is it okay? Okay, so here's the mathematical way to write it. Okay, so suppose that a over b is a rational number. Here we add written in its lowest terms. It means you can cancel whatever you can cancel. There's no common factor in a and b, right? In particular, there's no common factor of 2. Okay, so you start from here. You start from a over b, which is in the lowest terms, okay, such that whose square is 2. Okay. Then it follows that a squared is 2 times b squared. Then, as we discussed a few minutes ago, hence a squared and consequently a is even. It's an even number. So we write a as 2 times m for a suitable integer m. And then we obtain a squared, which is 2m squared, equal 2 times b squared, right? And then that is the same thing. 2 times m squared is b squared. But this shows b, in turn, must be even, right, as we argued, which contradicts the fact that a over b is in lowest term, right? So therefore, no such a over b exists. So this is the proof of square root 2 is irrational. Any questions? Okay. So it's a simple example, but I think this is one of the best theorems, right? Okay, so that's the first example, classical example. So the second example I'm going to show you, or mentioned by Hardy, is this: is the theorem attributed to Euclid. So the theorem says there are infinitely many prime numbers. I have defined prime number. The prime numbers are those. The number is bigger than 1, and the only factor of that number is 1 and itself. For example, 3. 3 is a prime number. 2 is also a prime number. So Euclid shows there are infinitely many prime numbers. Okay. So again, this picture is coming from this is from the painting by Raphael from the School of Athens. This guy is supposedly Euclid. Okay, so before that, I want to remind you about division, because for natural numbers you can add, you can multiply, but usually you don't talk about division because sometimes the quotient of two natural numbers is not a natural number anymore, right? So I want to remind you some easy fact about division or quotient and remainder, all these things. Okay, so suppose n and m are integers. You can think of them as natural numbers. Okay, so we say that n divides m, written in this form: n with a stroke, a vertical stroke, followed by m. So this reads as n divides m. If m is a multiple of n, right? In other words, how to say? If you use n to divide m, you get a whole number, right? So this is the meaning: n divides m. We say n divides m if m is a multiple of n. Okay. So if there's an integer k, so that n times k is m. Okay. Now let's do a simple exercise, which I'm going to use it. So suppose n divides two numbers, n divides m1 and n divides m2. I want to convince you n will divide its difference, m1 minus m2. Okay? So let's treat this as an exercise of understanding the definition. So n divides m1 means m1 is a multiple of n, right? So m1 is n times some number, whole number k1, right? And n divides m2 means m2 is a multiple of n. So m2 is n times some other whole number, k2, right? So look at the difference, m1 minus m2. So m1 minus m2 will be n times k1 minus n times k2, right? So taking out the common factor, you get n times k1 minus k2. But the thing in the bracket is still a whole number. So m1 minus m2 is also a multiple of n, right? So n divides the difference. Okay? So in particular, at the final part of the proof of Euclid theorem, I'm going to use this fact. Suppose a number, p, divides n, and p divides n minus 1. I conclude that p will divide its difference, right? Here it says if n divides two numbers, then n divides the difference. So now in particular, I want to apply it to, okay, the choice of letter are messed up. So if p divides two numbers, n and n minus 1, then p would divide its difference. But n and n minus 1, the difference is 1, right? So p would divide 1. Okay, so I'm going to use this fact in 5 minutes later, okay? Okay, now come back to Euclid theorem. We want to show that there are infinitely many prime numbers. Okay, again, there's no obvious direct proofs. I mean this. Usually, if I claim there exists something, I would show you the thing, right? As justification. That's the evidence. But here I need to show you infinitely many things, right? The claim is there are infinitely many prime numbers, so I need to give you infinitely many numbers. But it's very hard, right? I can give you 5, I can give you 7, I can give you lots of prime numbers, but I can't give you, it's difficult to give you in one shot infinitely many numbers, right? So no obvious direct proofs. So perhaps we can try to use proof by contradiction, right? So the finest weapon of mathematicians. Okay, so let's assume there's only finitely many, right? Suppose it's not the case. There are infinitely many prime numbers. It means there's finitely many, right? So let's assume there are only finitely many prime numbers. So we know that 2 is prime, 3 is prime, and so on and so forth. So suppose the prime number stops, right, at after you count t many, and then no more, right? So say, so suppose these are the whole collection of prime numbers, and then let's see what happens. Okay. Now it certainly says all integers bigger than the last prime number is no longer prime, right? Because that's the biggest prime. If you are larger than biggest prime, you are not prime. Okay? But okay, here is a fact I assume you know. You know that every integer can be expressed as a product of prime numbers. They call the prime decomposition. For example, 10 can be written as a product of 2 times 5. So 2 is a prime, 5 is a prime, right? So for any natural number, either is a prime or it's a composite. If it's composite, you can factorize them. But keep factorizing, in the end you get something which is a prime, right? So this fact I assume you know. Okay, so every integer can be called decomposed or factorized or expressed as a product of primes. Okay. So now any number bigger than this supposedly last prime should be divisible by one of the primes, right? Because the fact says any integer can be expressed as product of primes. So look at the integer bigger than this pt. It is a product of primes, so it should be divisible by one of the primes. Okay? But is this true? So you can try how about this number? Right? Suppose, okay, look at this particular number, which is the product of these collection, P1 times P2 times all the way times to PT, and after that you add a 1. Okay? So look at this number. Can this number be divisible by one of the primes? Try again. So we are doing this discussion. So suppose there's only finitely many prime numbers, which are P1, P2 up to PT. These are the exhaustive list of all prime numbers. Now the challenge is, consider this number. You multiply these collection together, and then you do this nasty thing, add a 1. Okay? So look, consider this number. So we try to show that this number is not divisible by any of the primes. So therefore it contradicts to the fact. Okay? So here's the discussion. Now here's the proof. Right? So what's wrong with that number? So here you'll see what's wrong with that number. Okay, so the proof goes like this. It's a proof by contradiction, so we start from this line. Suppose, to the contrary, that there are only a finite number of primes. So let these primes be P1, which is 2, P2 is 3, and all the way to PT for some t, right? Because there are only finite many, we can list them out. Okay, so now let n be this nasty number, be the integer of the product of these p's plus 1. Okay, look at this number, capital N. Now certainly the capital N is not a prime because it is bigger than the biggest prime, so it's not a prime. So N is a product of primes, right? So let's consider one factor of N. Let Q be a prime number which divides N. Okay, so look at Q. But Q must be one of the PJs because this list is exhaustive. Every prime in the world are there. So Q is a prime, so Q must appear in the list, right? So maybe the Q is P sub R, right? Q must appear in the list, so Q is P something. So it's P sub R. So now we have P sub R is a factor of N because P sub R is this Q, but Q is dividing N. So Q divides N, so P sub R must divide N, right? On the other hand, P sub R appear in the list, so P sub R must divide this product, right? Because this is P1 times P2 times something, but include P sub R. So this is the whole product. So P sub R must divide this product, but this product is n minus 1 because capital N is this, this product is n subtract 1. So P sub r divides capital N, P sub r divides capital N minus 1. By the previous slides, I told you, so P sub r would divide the difference, right? So P sub r should divide N, take away bracket N minus 1, but it's 1. That's not possible because P sub r is a prime number. Prime numbers are bigger than 1. It cannot be a factor of 1. Okay. So we get a contradiction, right? But we are proving by contradiction. So whenever we see a contradiction, we are happy, right? So therefore, hence the number of primes is indeed infinite. Okay, so this is the second. So now for those of you who have seen this before, try this question. So in the proof, we look at some nasty number of the form bunch of product is a product of bunch of primes plus 1, right? Okay. So now consider the list. Okay, so here is the first prime plus 1, the product of first 2 primes plus 1, the product of first 3 primes plus 1, okay, product first 4 primes plus 1, so on and so forth. Now, are these things all primes? Okay, if you haven't thought about it, think of it. Right? By the way, whether the answer is yes or no, it doesn't change our proof. Our proof doesn't depend on this fact. Okay, our proof is a proof by contradiction, and is logically tight. No matter so whether there's something here not prime doesn't matter. It doesn't change our proof. Okay, so questions about the two theorem. Do you agree with Hardy? Okay, so what do I mean? So first, do you think these two are nice theorems? Whether it's the best or so these are really good theorems. Right? Also, do you believe that any person with reasonable intelligence can understand in 1 hour? Do you agree? Yes, right? Okay. Anyway, so okay, so I think I can cover a little bit more, then we take a break. So now, this is the second item. So we are going to talk about the size of a set, how to count the number of elements. Right? So the size of a set denoted by the, okay, looks like absolute value, but it stands for the size. It's a number of the distinct elements in A, in the set A. For example, A is this 1. A has these elements 1, 209 or 71, whatever. The size of it is 3 because it has 3 elements. Okay. Another example is look at the natural numbers between 1 and small n. There are exactly n of them, right? From 1, 2, 3. So if n equals 3, you have 3. If n is 2020, you have 2020, right? Okay, here we only discuss the size of a finite set. Next lecture, we are going to look at the story of infinite sets. That's a completely different picture. It's not obvious how to count infinitely many numbers. Right? So we at least in the next hour or next 40 minutes, we consider only finite sets. The sets you can count the number of elements. Okay. Okay. So now we want to count lots of. We will see several examples of counting. So we are going to use some fact about counting the union of two sets. Okay, so here's a starting point. Suppose I have two sets A and B, and they are, okay, the fancy word is disjoint, means they have no overlap. They have no common elements. A intersect B is empty. There's no element in both A and B. Okay, so then if you want to calculate the union, the size of the union, is you just add the number of elements in A plus the number of elements in B. Right? You just add them. Okay. So because it's safe to add them because there's no double counting. So you can just simply add them. Is this okay? So first, if I have two sets with no overlaps, then I can just simply, if I count the whole collection, I just add them, right? Okay, so now how about some set with overlaps? Can we count? Is there a formula like that to tell us what is the size of A union B if A and B has overlap? Well, you know, right? So this is called the principle of inclusion and exclusion. Some people call it inclusion and exclusion principle, but written in this way has a nice shorthand called PIE, called PIE, right? Principle of inclusion and exclusion. So look at, suppose I look at two sets, A and B, right? In general, the Venn diagram looks like this, right? So this is, the green set is A, the blue set is B. So this figure stands for is a Venn diagram for A union B, right? So the theorem says the total number in this figure is the number of elements in the green plus the number of elements in the blue, but you have to take away one copy of the overlap, right? You have to take away the intersection. Okay, so this gives us a way to count the number of elements. Okay, so now I'm a mathematician, so I'll prove everything. So I'll prove this. So why this is true? Well, I've just used the fact in the previous slide, right? Because look at the three regions, the shallow green, and then this overlapping part, and this shallow blue, right? These three regions are disjoint. They have no common elements, right? They have no overlaps. So by the fact we know the union, if I want to count the total number inside this A union B, is just a sum of the three regions, because the three regions has no overlap, right? So there's no double counting. So the size of A union B is the shallow green plus the overlapping plus the shallow blue, right? So this is A take away B. This part is the green, the shallow green, and B minus A is the shallow blue, and A intersect B is in the middle, right? So A union B is the sum of this. Now look at individual sets A and B. A is the circle to the left, right? So A is the shallow green plus overlap. So it's this, so it's this. And B, same reason. B is the shallow blue plus overlap. Now by these three equations, immediately you get A union B is, for example, if you add these two, A plus B, what do you get? You get A minus B plus B minus A plus two copy of these, right? So therefore, this guy is, so this is two copies of that, and then from this you can derive the theorem, right? Because he is the sum of first two plus one copy. So therefore, if you subtract one copy from here, you get A union B. Right? Okay, so it's an easy fact. Now, using this fact, it helps us to count some complicated sets. So we'll do a simple example first, then we'll look at more examples of inclusion-exclusion principle. So let's do this simple example, and then we take a short break. Okay. So the example says we want to find the number of positive integers which are less than 100, and they are multiples of 3 or multiples of 7. Right? So we have two sets. One is multiple 3, the other set is multiple 7. We want to count how many elements are in the union. Okay? Okay, so now this is a typical application of this principle of inclusion exclusion. So let A and B be the sets of multiples 3 and 7 respectively. And then the size of A is easy to count, right? Because these are the numbers, multiple 3 but less than 100. So it's, the size is just 100 divided by 3. You take the floor, you take the integer part. So you get 33. Similarly, the size of B is 100 divided by 7. You take the integer part, which is 14. So furthermore, the intersection happens to be the set of multiples of the product, 21. So this is actually because the 3 and the 7 has no common factor. So therefore, you can do this. Okay? So therefore, the intersection has size 4. Okay, now by the PIE, you get the sum of the size of A plus size of B, take away the overlap, which is 4, so you get 43. Okay. Here I use this square bracket, stands for the greatest integer less than or equal to x. Some people call it floor or something. Okay, so let's take a short break, and after that we continue to see slightly more complicated examples. Okay, so let's continue. We have seen the PIE for 2 sets. Now we can generalize to 3 sets, 4 sets, and so on and so forth. So let's look at 3 sets. So the claim was the size of A union B union C, right? There are 3 sets, A, B, C. So you have to do this inclusion, exclusion. Okay, so you have to include everything is A plus B plus C. So this is inclusion. But then you have to exclude. So you have to take away the pairwise intersection, the pairwise overlap. So you take away A intersect B, take away B intersect C, and take away C intersect A. So you exclude these things. But however, if you exclude all 3 of them, you exclude too much. You have to include something back. So the intersection of the 3 you have to include. So you have to add the common element of the A and B and C, right? So try again. So you have to add all the you have to add the A, B, and C, right? Include everything, and then you take away the pairwise overlap, and then you include the 3-way overlap. Right? So this is the inclusion exclusion. Then you'll see a pattern. Somehow include everything, take away pairwise, include 3-fold, exclude 4-fold or something. So that's the pattern. Anyway, so let's try to prove or justify this. Okay, so we want to show the formula is true. So let's apply the principle for 2 sets several times so that we get our conclusion. Okay, so now look at this. Now I want to compute the union of 3 sets. Now I think of them as union of 2 sets. So, but the first set is very big. It's A union B. So think of this as A union B, then union with C, right? So I can apply the PIE for 2 sets. I get this. So it's the size of first set plus the size of second set. Take away the intersection. Okay. So this is the PIE for 2 sets. Now this guy is a union of 2. A union B is a union of A and B. So I can apply this PIE to him. So this is the size of A plus size of B, take away the intersection. Right? Now copy down the remaining ones. Okay. Okay, now you see the A plus B plus C showed up. Right? Now we have to do something here so that we exclude those intersections. Okay, now look at this set, the size of bracket A union B intersect C. So here we have to use a law about sets. So it has a fancy name called distributive law, but you can check it by Venn diagram. Okay, so the law says the set bracket A union B intersect C actually is A intersect C union B intersect C. It's like you use a C you distribute the intersect C to A and then to B. Right? So this is called distributive law. I don't have time to draw the Venn diagram, but if you have doubts, I'll draw it after class for you. Okay, so you get this. So now it looks like union of 2 sets. So I use the PIE for 2 sets. So you get the size of first set plus the size of second set, take away the intersection, right? But now this time the intersection is easier. It's just A intersect B intersect C, right? Okay. So this term is, okay, the size of intersect C plus the size of B intersect C, take away the size of 3-way intersection. Okay. Now plug in this in here. Here is a minus sign. So I have minus this intersection minus the other intersection. Now this guy become plus, right? So if I plug in here, I'm done. Okay, so that's the justification. Okay. Now, here's the example, right? How do we apply this PIE for 3 sets? So here is a example. I don't know who made it, but okay. So at Durham High School, or whatever, there's a school. So there are 55 students, and they are in either algebra, which is A, biology is B, and C, chemistry. Right? They are in these classes. But the data we know is there are 28 in A, 30 in B, 24 in C. Now, A intersect B, the size is 8. B intersect C, the size is 16. And A intersect C, the size is 5. Okay, so these are the data given to us. So we want to know how many students attending all three classes. Okay? So in other words, we want to find the size of A intersect B intersect C. Okay. Well, this is a typical example, use PIE, right? So, okay, so we use capital A, capital B, capital C to denote the set of students taking algebra, biology, and chemistry. Okay. Now the data says, I already interpreted the data. Oh, maybe I didn't interpret this. So altogether, there are 55 students. So it means A union B union C is 55, right? The size of A union B union C is 55. So all other data are like that. I will not read it. So by this PIE for three sets, you know that the three-way intersection can be calculated by this formula. You just move the terms to around, then you get this formula. Then plug in numbers. So in the end, you get 2. So it means there's 2 students attend all three classes. Okay? In the tutorial, you'll see similar exercises. Okay. All right, so how about more, right? Then why stop at 3? Well, luckily on internet, I can find these. I couldn't find 6 or 2,000. Okay, so anyway, so you know this. And then mathematicians always like what happened in general, right? For arbitrary n. Well, okay, so you can do something like this. So basically, suppose you want to calculate the size of union of n sets, A1 up to AN. I will not read the terms, but the philosophy is, the idea is you include the single sets, the size of single sets, right? You add them up, right? So this is like A1 plus A2, size of A1 plus size of A2 plus all the way to size of AN. So this is inclusion. Then you exclude all pairwise intersections, right? All pairwise intersections, and then you have to include all three-way intersections. Then you have to take away all four-way intersections. Then include 5, take away 6, alternating. So in the end, you get, I don't know, it depends on, it's even and odd, so you get -1 to the n-1 power of the intersection, right? So this is the PIE for n sets. I don't think we'll see examples of this, but it's nice to know. So if you are good at mathematical induction, you can show it by mathematical induction. Okay, so now, so that's about counting and this PIE for say 3 sets and so on and so forth. Okay, so there are a few other concepts related to sets. So one is something called power set. So the power set of a set A, so capital A is a set. The power set of A denoted by, okay, so this is curly P, come from power. Right? The power of A is a set of all subsets. Okay, so power set of A collect all the X, capital X, such that capital X is a subset of capital A. Okay, so for example, we know that empty set is a subset of anything, right? So empty set is a subset of A, and A itself is a subset of A, right? So therefore, empty set is an element of the power set of A, capital A, And A itself, capital A itself, is element of power set A. Let's do one more example. Suppose I have a set S which is 0, 1 of two elements. What is the power set of S? Okay, so we want to find out all subsets of S, right? So let's do it systematically. So first, we must include the empty set, right? Which is the subset has 0 elements, okay? And then we must include the subsets which has 1 element. So S only have 0 and 1. So if you collect all the subset of 1 element, so you get this, the set of 0 and set of 1, which are the only two subsets of S having 1 element. Okay. Then after that, let's include all subsets of S which has 2 elements. Well, S itself only have 2 elements, so you get S itself, right? So in this way, you get 4 elements, and no more, because here we exhaust everything. Right? Now, so let's just look at 0, 1, 2, for example. What is the power set of the set of 0, 1, 2? So empty set is there, and then you look at the singleton sets, right? The subsets having 1 element. So you get set of 1, set of 0, set of 1, set of 2. Okay. And then you look at the subset. Let me write it. Sorry. Where's the pen? Sorry, somebody took away the pen you turned on. Okay, anyway, so I'll use maybe okay. So the example I'm trying to show, hopefully I can write it. If I can't write it, then so let's consider. No, I need the pen for the PDF. Well, okay, so sorry. So let me try one more time. Okay. So let's consider a set. Let's call it B. B is 0, 1, 2. I want to calculate the power set of B. Okay. First, I already said we include empty set, which is a subset contain 0 element, no elements. Okay. And then we look at the subset contain just 1 element. So it's a set of 0, set of 1, set of 2. Then we look at all subsets of B having 2 elements. So it's just 0, 1, 0, 2, and 1, 2. Right? Then we look at the subset of B having 3 elements. So it's just 0, 1, 2. So altogether you have 8 elements. Right? So that's the examples. Okay. Okay, so and then we move on to our next concept, which is we look at functions. Okay, here I'm sure you have seen examples, but let's go through it again together. Right? Let's do things slowly. Okay, so the usual way, probably in JC, you learn functions like this. So the function written in this way, f is a function from A, capital A to B, denoted by, you draw an arrow here, from A to B, is a relation between elements in A and in B, right? So in other words, it associates each small a in capital A, one and only one element, small b in B, in capital B. Sorry, try again. So what is a function? What is a function? The function is some kind of association or some kind of link, so that for the element in the, we will call it domain. In the capital A, we will link a unique element in B, right? So this is the description. So it's kind of correspondence or connection or link, okay? So if F associates B to A, then we write B is F of A, okay? And say B is an image under F of small a, right? So the capital A is called the domain of F, and the capital B is called the codomain of F. Maybe this codomain is new to you. Okay, the set, the small b in capital B, so that there is a small a in capital A, Fa equal B, is called the range of F. Okay, so there are some remarks, right? So the key for the concept function is single value. Because for each small a in capital A, you only have one. It's a single value. You only have one value associated with this A. Okay. So you may ask, why not? Why do we restrict ourselves to one value, single value? Well, there's justification, because if it's more value, right? Suppose one point is associated with several points, we can study them separately, right? Suppose you want to study three-valued functions. Well, this is just three single-value functions. So if you understand what's going on for single-value functions, then consider this three-value function as three of them, and then you didn't lose anything, right? So we do this divide and conquer. So if we understand everything for single-value functions, then we sort of understand the multi-value functions. Okay, so that's one justification. And why? Okay, so here there are two concepts. One is codomain, one is range. Right? Codomain is like how to say? It's like a big area. Then the range is where you actually hit. Right? So why do we need this difference? Why don't we just require the codomain is range? Right? Then that saves lots of things. It's symmetric and so on. No, but well, in real life, it's not like this, right? Because, for example, in real life, suppose I ask you to measure the temperature every hour, right? So I give you, so I'm considering a function. So the function f is is defined on the 24 hours, like 0 midnight, 1 o'clock, 2 o'clock. So f is a function whose domain is the hour. Okay. Now the range will be temperature, right? So I don't know. Singapore is 29 degrees, maybe 28 degrees, and 30 degrees, and so right. So I'm asking you. I'm defining a function f, which is the temperature in Singapore at the hour. Okay, now it's impossible to have the exact range. I mean, you wouldn't, how to say, it's more reasonable. I give you a region, like, so the codomain, I know the codomain of this function, the temperature function, will be from 26 to, I don't know, 34, right? Because Singapore weather usually like that. Now the range actually depends on the day, right? Some day maybe it's just 29 and 30. Some day maybe it's like 23, no, not 23, 27, 28, 29, 30, 31, right? So it's very hard to know beforehand what the range of function is. So it's more convenient to have a codomain, right? So you know roughly where you are, but the measurement give you the exact range. Right? So this is not mathematical, but I'm trying to explain that there's a reason to do things like that. Okay. Now, functions has other names called maps and mapping operation and so on and so forth. Okay, so there are lots of example functions. So in calculus or in physics, functions are usually from real number to real number. Right? For example, we have seen linear functions like ax plus b. So the graph is like a line, right? We have seen this quadratic functions, right? It's like a parabola. We have seen exponential functions or power functions like this, x to the power of a, okay? And polynomials. So these are functions depending on x, right? And also you have lots of the exponential function, log function, sine function, cosine. So these are all examples of functions. Okay. So in engineering or in physics, you see lots of things like this. Okay. So these are coming from real life, right? Now, sometimes in mathematics we study maybe some artificial functions. For example, this function, I don't know, probably is not so common, but still you can imagine we may encounter it. So these are piecewise defined. So maybe the function, okay, look at this function. The function is defined on 3 pieces, right? So at x bigger than or equal to 1, it is x minus 1. And when x is somewhere else, it's x squared. And then when x is less than minus 1, is 1. So this function is defined piecewise. It's like you have 3 pieces, and then you put them together. Right? So this is also a function. Okay. So I will not draw the graph. I don't have time. Now, to illustrate especially when I talk about injective or surjective functions, sometimes it's convenient to have some artificial. So I'll just draw, it's like I draw the Venn diagram. I'll draw pictures like this to indicate functions. So I'll call it cooked function. I don't know. It's artificial. I made it. Okay. So we made this. For example, let's consider this function f, right, represented by this picture. So I have domain A, capital A, which is ABC. I have codomain B, which is 1, 2, 3, 4. Right. So the function I'm going to describe is a way to associate elements from capital A to capital B, right? For element small a, I associate with 2. For element small b, I associate with 4. For element small c, I associate with 2 again. Right? So this is an example of a function. Okay? Now, for the same a and b, I can define another function. Right? I have a different way of associating things. So I can associate a to 2, but b I can associate with 1, right? And c, instead of associate with 2 again, I can associate with 4. So I get another function, right? So these are also example functions. Okay, so is this all right? So there are examples. Okay, now I want to define 2 or 3 kinds of functions, which are very, very useful in mathematics and in engineering. Okay, so one description is, one kind of function is called injective functions. Some people call it one-one function. Okay, so a function f from a to b is called injective or one-one, one-to-one. If okay, so the mathematical formula is this. For every x1, x2 in A, if x1 is not x2, then f of x1 is not f of x2. Well, this is too mathematical, but in words it says distinct points maps distinct points. You don't map 2 points into 1, right? So if x1 and x2 are distinct, after you take f, they are still distinct. So you send different points to different points. So this is the meaning of 1, 1. Now, very often is easier to work with is contrapositive. Right? You see here I have 2 negations. So it's a negation of this implies negation of that. But when we study logic, we know P implies Q is the same as not Q implies not P. So you by contrapositive, you can flip this, get rid of the negation. Right? Sometimes it's easier to work with equality rather than negation. Right? So we have an equivalent way of describing one-one functions. Now, whichever way, they are equivalent, so whichever way is useful, is convenient, we'll use whatever. Okay, so look at example. A function from real to real defined by f of x is x squared. So this is not injective. You see the I don't have the pen. That's so you see the parabola. So the graph of this function is a parabola. Then you have f1 and f minus 1 are the same, because f1, if you square is 1, and minus 1 you square is also 1. So 1 and minus 1 are distinct, but after you take f, they become the same point. So this is not injective. Now on the other hand, if you look at the cubic function, g of x is x squared, then this is injective, because distinct points will, because this if you draw the curve, this is strictly increasing. So distinct points map to distinct points. Now I can also illustrate the concept using these cooked examples, using the artificial examples. For example, here, the f I just defined, right? I have 2 points, A and C, mapped to the same point. So this is not injective. Right? Injective says distinct points go to distinct points. This f violates that. This f sends distinct point A and C to the same point. So therefore f is not injective. Now look at this g. G, it turns out g is injective, because the arrow starting from different points will shoot to different points. Right? So distinct points go to distinct points. Right? So this is injective. Now there's a related concept called surjective. Surjective, let me read the definition first. So a function f from a to b is called surjective, or some people call it onto, if for every y in the codomain b, there is an x in a such that f will send x to y. Fx is y. So in other words, if the range it happens to be the codomain, then f is called surjective. Okay. Now, same pair of example. So look at the function f from reals to reals defined by x squared. So this is not surjective, because the codomain here is R, is a real number. Now this function does not hit everything in the codomain. For example, minus 1 is in the codomain, but minus 1 is never a square of real number. So this fx equal x squared is not surjective. Okay. Now this cubic function turns out to be surjective. Because you give me a number, I can find we call it pre-image. Right? Suppose you give me anything in the codomain. I want to convince you I can hit the thing you give me by G. Okay, let's try. You give me 2020, 2020. Okay, what is the G? What is the point A so that GA is 2020? I'll take cubic root of 2020 because there's always cubic root. So I take cubic root 2020. That is my A. So G of cubic root 2020 will hit 2020. Right? Now obviously 2020 is just any number. I can change it to any B or whatever. Okay. Now, do I have? Okay, so here's the example. Now, look at this function. from A, B, C, D to 1, 2, 3, defined in this way. Okay? Is this surjective? Do I hit everything in the codomain? Yes, right? Because for every element in the codomain, which is 1, 2, 3, it was hit by some arrow. So this is the capital F is surjective. Now, how about this picture, capital G? Suppose I define a function this way. So I claim G, capital G, is not surjective because the number 2 in the codomain is not in the range because no arrow hit number 2, right? So this demonstrates capital G is not surjective. Okay. Now, once you know surjective, injective, then you know you can combine them, right? So this is called bijective. So a function f from A to B is called a bijective if it is both injective and surjective, right? So the idea is the bijective is a perfect match. You match the points in A and B in a very nice way. You never overlap, you never double hit, and you never miss, right? Never double hit means you are 1-to-1. You are injective. You never miss is you are surjective, right? So this is for example, just now we've seen this function, cubic function, gx defined on reals, such that g of x is x cubed is bijective, because we said we saw it is both injective and surjective. Okay, so more examples. Again, maybe I'll just look at the picture, right? So look at this f. So this capital F, defined this way, is neither injective nor surjective, right? So this is not bijective, right? Because it's not injective. You have a double hit. This point 3, you hit by 2 arrows. It is not surjective because you missed the 4, so it's not surjective. Okay. Now on the other hand, this G, capital G, is a bijection because different arrows shoot to different points. So this is injective, and we did not miss any points here, so it's surjective, right? So for the Cook example, it's very easy to illustrate the idea. Okay. I guess I will not. Okay, I'll leave this to the next lecture. But maybe I'll say it so that you'll know what I'm going to say next time. So there's a fact in number theory. It's called the pigeonhole principle. Pigeonhole, PHP, pigeonhole principle. So it says this. Suppose you have two natural numbers, m and n, and m is bigger. So for example, m is 5, n is 3, right? So the pigeonhole principle says any function from a bigger domain to, look at the functions from m numbers, 1 ... to m, to n numbers, 1 ... to n, right? But if the domain, the size of the domain is bigger than the size of the codomain, and then the f cannot be injective. This looks very mathematical, but the explanation was very intuitive. So the name pigeonhole comes from this. Suppose you have m pigeons, fly to n pigeonholes. If the number of pigeons is bigger than the number of holes, some pigeon will share the same hole, right? So it's never 1-to-1. So the name comes from this example. Suppose, okay, so think of m as 2020, right? And n like 2019. So if you have this many pigeons and this many pigeonholes, right, then you cannot have injection. You must have double hit. So there are at least one pigeonhole which will get more than one pigeon, right? So it's very intuitive. So we next time we'll see more about this pigeonhole principle, and then we'll move on to something more abstract. So we'll talk about infinity, I guess. So so we'll see more math, more mathematics, and probably it's more optional. It's but I think I like to talk about infinity. So so next time we'll finish this part, and then we'll talk about infinity. Okay, so I'll stop here for today.